In an industrial plant, many different kinds of instruments can be used together as a system to control the process variables that are associated with the production of products. Instrument systems are important because without them, it would be difficult for operators to keep up with every process variable in the plant at the same time. Instrument systems monitor and adjust process variables at key points to keep the plant working safely and efficiently. Instruments are devices used to measure, indicate, or control a process variable, or transmit information about a process variable. An instrument system is a group of instruments and associated devices that work together to continually monitor a process variable. Some systems also control the value of the process variable. For example, this tank is part of a system that supplies water to several process systems in a plant. In order for a continuous supply of water to reach the various systems, the level of water in the tank must remain within a specific range. To make sure that this is achieved, the water level in the tank is monitored and controlled by an instrument system. This instrument system includes a transmitter, which senses the value of the process variable that's being monitored, in this case, the level of the water in the tank. The transmitter sends a signal, which is proportional to the value of the process variable, to other instruments in the system. This instrument system also includes an indicator, which shows the current level of water in the tank, and a recorder, which provides a record of the water level over a period of time. An instrument system may also have one or more alarms. Alarms are activated when the value of the process variable being monitored reaches a point that requires operator attention. In this instrument system, the alarms are activated when the water level in the tank is either too high or too low to ensure safe continuous operation. Alarms can be either visual or audible. Often, they're both. For example, this controller measures the signal it receives from the transmitter that represents the present value of the process variable and compares it to a preset value. This preset value is called set point. In this case, set point is the desired water level in the tank. If the signal matches the set point, the output from the controller does not change. However, if the signal is above or below the set point, the controller sends out a corrective signal. This signal goes to the final control element in the instrument system. In this case, the final control element is a level control valve that can be opened or closed by an actuator. This valve controls the water level in the tank by increasing or decreasing the flow of water into the tank. In this topic, we used a system that monitors and controls the water level in a tank to identify and describe the components of a basic instrument system. Now let's try some practice questions. An instrument system is a group of instruments and associated devices that work together to continually monitor a process variable. Some systems also control the value of the process variable. Alarms are activated when the value of the process variable being monitored reaches a point that requires operator attention. Since operators can't monitor all the different instruments associated with a process at the same time, most instrument systems contain alarms and other protective devices. Each alarm is designed to alert the operator when a process variable changes beyond an acceptable range. For example, the low-level alarm in this instrument system is activated when the water level in a tank falls below a predetermined minimum level. The high-level alarm is activated when the water level rises above a predetermined maximum level. Alarms can be visible, they can be audible, like this siren, or they can be both visible and audible. An alarm can respond indirectly to a condition if it's connected to the instrument system so that it monitors the signal from the transmitter, or directly if it's connected directly to the process being monitored. Alarms are usually activated by electrical switches, which are operated by sensing devices connected to the process. The sensing device can be mechanical, such as this pressure switch, which uses a Bourdon tube to respond directly to the pressure in a tank. Or the sensing device can be electrical, such as this thermocouple, which generates a voltage proportional to the temperature that it measures. In either case, when the value of the process variable reaches a specific point, The signal from the sensing device operates the switch, which activates the alarm. Each switch is able to operate in response to only one condition. For example, if the instrument system that monitors the water level in a tank has both a high-level alarm and a low-level alarm, each alarm has a separate switch. Each switch is set to operate when the water in the tank reaches a specific level. In addition to activating alarms, switches may also activate backup systems. For example, if this pump, which supplies water to a holding tank, fails, the water level drops to a point at which a switch activates the low-level alarm and activates a standby pump to help bring the water level in the tank back to set point. A switch may also be used as an interlock. An interlock ensures that a predetermined set of conditions exists before the status of equipment is changed to prevent equipment damage or harm to personnel. For example, this fan could be damaged if it's operated without proper lubrication. To prevent damage, an interlock pressure switch opens to shut off the fan's motor when the oil pressure in the motor is too low. The switch remains open to keep operators from turning on the fan by mistake until the oil pressure is high enough for normal operation. Controllers are devices that initiate action necessary to regulate the value of a process variable. In this water supply system, the controller receives a signal from the transmitter. The signal represents the level of water in the tank. The controller compares the transmitter's signal to the desired water level or set point. If there's a difference between the transmitter signal and set point, the controller sends a corrective signal to the final control element. In this case, the final control element is a flow control valve. Based on the corrective signal, the control valve opens or closes as necessary to regulate the flow of water into the tank and bring the water level back to set point. Controllers can be classified in several ways. For example, they can be classified by the process variable that they control, by whether they're electric or pneumatic, by functions they perform in addition to controlling the process variable, and by their location. The controller in this water supply system controls level. It operates by receiving a pneumatic signal from the transmitter, comparing that signal to set point, and sending a pneumatic signal to the final control element if necessary. So it can be referred to as a pneumatically operated level controller. Some controllers have a chart to record process variable values over a period of time. This controller could be called a recording controller. A controller can also be identified by its location. A controller that's located near the process it regulates is a local controller. Other controllers may be located some distance from the process, such as in a control room. These controllers are called remote controllers. Many controllers can operate in two different modes, automatic and manual. The controls and indicators used to switch from one mode to another are located on the controller. For example, this controller has a vertical scale with two pointers, a horizontal scale with a pointer, a set point adjustment knob, a thumb wheel used to adjust the final control element, and a selector switch used to change between automatic and manual control. Basically, the bottom portion of this controller is used during manual operation, and the top is used during automatic operation. In automatic control, or auto, an operator can adjust the set point by using the set point adjustment knob. The set point is indicated by one of the pointers on the controller's vertical scale. In automatic control, the controller compares the signal it receives from the transmitter to set point and generates an output signal that maintains the value of the process variable at set point. The value of the process variable is indicated by the second pointer on the vertical scale. When a system is not operating in a normal mode, an operator may need to take direct manual control of a process variable. In manual control, the operator sets the controller output signal directly by using the thumb wheel to adjust the position of the final control element as indicated on the horizontal scale. After the controller output is set, it will remain constant. This keeps the final control element in the same position until the setting is changed by the operator or until the controller is set to automatic operation. For example, this controller can be switched to manual operation at any time. However, for a smooth transfer back to auto from manual, the value of the process variable and the value of set point should be the same. Otherwise, rapid shifts in control action called bumps can occur. Bumps can adversely affect process operations, and they can sometimes damage equipment. To avoid bumps, the values of the process variable and set point should be equalized before a switch is made from manual to auto. A bumpless transfer can be done in one of two ways. In some cases, the value of set point is adjusted until it matches the value of the process variable. In other cases, the thumb wheel is used to adjust the position of the final control element until the value of the process variable is changed to match set point. Regardless of which method is used, once the two values match, the selector switch can be moved from one control mode to another without causing a bump. In this topic, we took a look at instrument system alarms and how switches may be used to activate alarms or backup systems or to act as interlocks. Finally, we saw how a controller can be identified, and we examined some of the steps necessary to switch a controller from one mode of operation to another. Now let's try some practice questions. Alarms can be visible, they can be audible, like this siren, or they can be both visible and audible. Alarms are usually activated by electrical switches, which are operated by sensing devices connected to the process. The controller sends a corrective signal to the final control element. In this case, the final control element is a flow control valve. This controller can be switched to manual operation at any time. However, for a smooth transfer back to auto from manual, the value of the process variable and the value of set point should be the same. Otherwise, rapid shifts in control action called bumps can occur. Bumps can adversely affect process operations, and they can sometimes damage equipment. To avoid bumps, the values of the process variable and set point should be equalized before a switch is made from manual to auto. Valves regulate the flow of gases and liquids in process systems. A valve that is operated automatically to throttle flow is usually referred to as a control valve. The control mechanism in a control valve is the valve's disc. The disc works basically the same way as a disc in a manually operated valve. Its operation can be either linear, as in this globe valve where the disc moves up and down to regulate flow, or it can be rotary, as in this plug valve where the disc rotates to open and close the valve. This is a typical control valve. The valve body contains the disc and the seat. The valve stem is attached to the disc so that the disc can be moved up and down to open and close the valve. The upper end of the valve stem is connected to an actuator. The actuator provides the power to move the valve stem in response to signals from the controller. Many different actuators can be used with control valves. Three general types are pneumatic, hydraulic, and electrical. The actuator on this control valve is a pneumatically operated diaphragm actuator. This type of actuator is commonly used in many process systems. An actuator is commonly operated by a corrective signal from a controller. However, in some cases, as in this pneumatic diaphragm actuator, the air pressure from the controller's signal alone is not enough to operate the actuator. To overcome the forces of friction in the actuator and the valve stem, and the fluid pressure against the valve disc, an actuator can be operated by a separate supply of higher pressure air. The higher air pressure is regulated by a valve positioner. If we move the positioner to one side, we can see that a mechanical linkage joins the valve stem to the positioner. This linkage, often called the feedback linkage, indicates the valve's position to the positioner. When the process variable in this system needs to be adjusted, the controller sends a pneumatic signal to the positioner. Then the positioner regulates the separate supply of higher pressure air to the actuator to move the valve to a new position. As the valve stem moves up or down, it moves the linkage. When the linkage indicates to the positioner that the valve is in the position called for by the controller, the actuator movement is stopped. In addition to valves, there are many other types of final control elements. Two of the most common are dampers and motors. Dampers, which are often called louvers, use a number of adjustable parallel vanes or blades to control the flow of air and other gases. In some systems, dampers have a pneumatic actuator with a positioner that controls the position of the vanes. During operation, when the positioner receives a signal from a controller, it supplies air pressure to the damper actuator. The actuator then opens or closes the vanes to position them according to the signal from the controller. Motors are also used in some process systems as final control elements. Motors provide the driving force to move, operate, or position components. For example, this variable speed motor is used to run a conveyor. Changing the electrical power supplied to the motor changes its speed, which slows down or speeds up the conveyor. While some motors are variable speed motors, many of the motors in a plant operate at only one speed. The output speed from a single speed motor can be controlled by connecting it to the process through a variable speed coupling. In this case, the coupling acts as the final control element. For example, this fan supplies air to a process system. It's connected to a motor through a coupling that can regulate the speed at which the fan blades rotate. When the supply of air from the fan needs to be changed, a signal is sent from the controller to an actuator connected to the coupling. The actuator adjusts the coupling to alter the speed of the fan, which changes the amount of air supplied to the system. In this topic, we saw how a control valve can be used as a final control element. We also looked at how pneumatic actuators and positioners are used to position valves. Then we examined some other components that can be used as final control elements. Now let's try some practice questions. The control mechanism in a control valve is the valve's disc. The disc works basically the same way as a disc in a manually operated valve. Its operation can be either linear, as in this globe valve where the disc moves up and down to regulate flow, or it can be rotary, as in this plug valve, where the disc rotates to open and close the valve. If we move the positioner to one side, we can see that a mechanical linkage joins the valve stem to the positioner. This linkage, often called the feedback linkage, indicates the valve's position to the positioner. The output speed from a single-speed motor can be controlled by connecting it to the process through a variable speed coupling. In this case, the coupling acts as the final control element.
During many processes, variables that relate to a material's physical and chemical composition are measured. These variables, called analytical variables, are typically measured with instruments called analyzers. The information provided by analytical measurements is used to make sure that process requirements are met. Sometimes it's necessary to determine the relative amounts of substances in solutions or mixtures. One way to do this is through density and specific gravity measurements. Density is the weight per unit volume of a substance. It's commonly expressed in units such as pounds per cubic foot or grams per cubic centimeter. For example, the density of water is 62.4 pounds per cubic foot, or 1 gram per cubic centimeter. The densities of different substances can be compared in terms of their specific gravities. Specific gravity is the ratio of the weight of a fixed volume of a substance to the weight of an equal volume of water at a standard temperature of 4 degrees Celsius, the temperature at which water is most dense. For example, the specific gravity of this alcohol can be determined by dividing its density, 0.79 grams per cubic centimeter, by the density of an equal volume of water, 1 gram per cubic centimeter. When the division is done, the units of measurement cancel out, leaving a specific gravity value of 0.79. This means that alcohol is 0.79 times as dense as water. Now, the density and the specific gravity of a solution can vary according to the relative amounts of substances in the solution. For example, if you mix alcohol and water, the specific gravity of the solution will depend on how much of each liquid is used. Since alcohol has a lower specific gravity than water, the more alcohol that's used, the lower the specific gravity of the solution. Density measurements are often used to determine the purity or concentration of salt solutions, petroleum products, and acids. One way to take these measurements is to use a hydrometer. Hydrometers vary in design, but this one is basically a sealed glass tube with a weight at one end and a specific gravity scale enclosed in a stem on the other end. A hydrometer works on the principle that a floating object displaces an amount of liquid that's equal to its own weight. Based on this principle, the depth at which a hydrometer floats in a liquid is an indication of the liquid's specific gravity. For example, this hydrometer floats in a container of acid. This acid is relatively dense, so the hydrometer displaces only a small amount of the liquid and floats near the surface. The hydrometer's scale indicates a specific gravity value of about 1.6. Now, if the acid is replaced with a less dense solution, the hydrometer displaces more of the solution and sinks lower. As a result, the hydrometer's scale indicates a lower specific gravity value. The density of a liquid can be affected by different factors, one of which is temperature. For that reason, many hydrometers are calibrated for a standard temperature of 77 degrees Fahrenheit. Also, some hydrometers are used with a thermometer so that temperature compensations can be made. For example, this thermometer has a scale that lists correction factors for temperature compensation. To obtain a specific gravity reading, the temperature is first read on the right-hand scale, and then the equivalent correction factor is taken from the left-hand scale. For temperatures above 77 degrees, the correction factor is added to the hydrometer reading. For temperatures below 77 degrees, the correction factor is subtracted. With some methods of density measurement, the entire measuring procedure must be repeated every time a reading is needed for a new sample of solution. But some systems, like this density bubbler system, allow for continuous density measurements. The operation of this density bubbler system is based on the fact that the difference in pressure across a differential pressure, or DP cell, depends not only on the difference in the length of two bubbler tubes, but also on the density of the liquid in the tank. During operation, regulators are used to adjust airflows through the two bubbler tubes until bubbles slowly rise from each tube. The air pressure needed to clear each tube of liquid is equal to the pressure exerted by the liquid above the bottom of that tube. Since the tubes extend to different depths, there's always a slight difference in the air pressure supplied to the tubes. So there's always a slight difference in pressure across the DP cell. As long as the liquid is maintained at a constant level by an overflow pipe, the difference in pressure across the DP cell caused by the difference in tube length remains constant. This means that any change in differential pressure across the DP cell can be attributed to a change in the density of the liquid. An indicator that's connected to the DP cell displays the density indication. Often, the density indication is expressed as a % concentration of a particular substance in the liquid. Some process liquids are too corrosive for certain density measuring devices. In these situations, a device such as this radioactive density analyzer may be used. A radioactive density analyzer measures the density of a liquid without coming into direct contact with the liquid. During operation, a radiation source sends a small amount of radiation through a pipe containing the liquid that's being measured. The amount of radiation that reaches a detector on the other side of the pipe depends on the density of the liquid. The denser the liquid, the less radiation reaches the detector. The detector may display the radiation measurement as a density value for the liquid, or as a concentration value for a particular substance in the liquid. In this topic, we talked about what density is and how it differs from specific gravity. We also looked at how several density measuring devices work. Now let's try some practice questions. Density is the weight per unit volume of a substance. It's commonly expressed in units such as pounds per cubic foot or grams per cubic centimeter. A hydrometer works on the principle that a floating object displaces an amount of liquid that's equal to its own weight. A hydrometer works on the principle that a floating object displaces an amount of liquid that's equal to its own weight. The operation of this density bubbler system is based on the fact that the difference in pressure across a differential pressure, or DP cell, depends not only on the difference in the length of two bubbler tubes, but also on the density of the liquid in the tank. A radioactive density analyzer measures the density of a liquid without coming into direct contact with the liquid. During operation, a radiation source sends a small amount of radiation through a pipe containing the liquid that's being measured. The amount of radiation that reaches a detector on the other side of the pipe depends on the density of the liquid. The denser the liquid, the less radiation reaches the detector. Often, it's necessary to monitor the concentration of suspended particles in processed liquids or gases. For example, wastewater is normally checked to make sure that it's been properly treated before it's returned to the environment. One way to check the purity of a liquid or a gas is to measure its clarity. Clarity is the measure of how clear or transparent a substance is. Clarity can be measured using different types of clarity analyzers. Clarity analyzers measure light and a substance's ability to let light pass through it. Three factors that affect how light passes through a substance are color intensity, turbidity, and opacity. Color intensity is the strength of a particular color. Turbidity is the cloudiness of a mixture. And opacity is a measure of the lack of penetration of light through a substance. Turbidity and opacity are related. As the turbidity of a mixture increases, less light is able to pass through it. So as turbidity increases, opacity increases as well. Clarity analyzers measure a substance's ability to let light pass through it in different ways. For example, some analyzers provide clarity measurements based on color intensity. One such device is a colorimeter. A colorimeter measures clarity by comparing the color intensity of the solution being tested to a standard solution with a known color intensity. The standard solution is placed in the colorimeter first, and the colorimeter is adjusted to it. Then the sample solution is put in, and the color intensities of the two solutions are compared. The difference in the color intensities of the two solutions is proportional to the difference in the clarities of the two solutions. As a result, the clarity of the solution being tested can be determined. The cloudiness or turbidity of a liquid varies according to the concentration of suspended particles in the liquid. For example, this vial of liquid has few suspended particles and is relatively clear, while this one has a much higher concentration of suspended particles and is much more turbid. A clarity analyzer that measures the turbidity of a mixture is called a turbidity meter. During the operation of a turbidity meter, the liquid being tested passes through a special restriction that forms the liquid into a flat stream. A beam of light is then directed through the flat stream of liquid. Suspended particles in the liquid absorb and scatter some of the light, but the rest of the light reaches a light measuring device called a photometer. The amount of light that reaches the photometer depends on the amount of suspended particles in the liquid. The more suspended particles, the less light reaches the photometer. As a result, the light measurement from the photometer is an indication of the turbidity of the liquid. Here, the light measurement is expressed as a percentage of turbidity called Formyson turbidity units, or FTUs. But turbidity can also be measured as a percent concentration of suspended solids. While clarity measurements are often made in liquids, they can also be made in other process materials, such as the gases from a stack. One way to determine the clarity of a gas is to measure its opacity. Opacity is basically the opposite of clarity, and it can be measured using a device called an opacity meter. During the operation of an opacity meter, a light beam is sent through the gas being measured to a reflector, which reflects the light beam to a light measuring device called a photometer. Some of the light that's sent through the gas is absorbed or scattered by suspended particles in the gas, but some of the light reaches the photometer. The photometer senses the amount of light and sends a proportional signal to an indicator, which displays the opacity of the gas as a percentage value. The more suspended particles there are in the gas, the higher the percentage of opacity. In some plants, opacity measurements are used to monitor particulates in gas being discharged to the environment. Operators often use those indications to make necessary operating changes. In this topic, we talked about what clarity is, and we looked at how three types of clarity analyzers work. Now let's try some practice questions that relate to this material. Three factors that affect how light passes through a substance are color intensity, turbidity, and opacity. Color intensity is the strength of a particular color. Turbidity is the cloudiness of a mixture. And opacity is a measure of the lack of penetration of light through a substance. Clarity analyzers measure a substance's ability to let light pass through it in different ways. For example, some analyzers provide clarity measurements based on color intensity. One such device is a colorimeter. A colorimeter measures clarity by comparing the color intensity of the solution being tested to a standard solution with a known color intensity. During the operation of a turbidity meter, The liquid being tested passes through a special restriction that forms the liquid into a flat stream. A beam of light is then directed through the flat stream of liquid. Suspended particles in the liquid absorb and scatter some of the light, but the rest of the light reaches a light measuring device called a photometer. The amount of light that reaches the photometer depends on the amount of suspended particles in the liquid. One way to determine the clarity of a gas is to measure its opacity. Opacity is basically the opposite of clarity, and it can be measured using a device called an opacity meter. Water is present in many process materials, as well as in the air surrounding process equipment. Measurements of water content are often expressed as humidity or moisture. Humidity is a measure of the amount of water vapor in a given volume of air. Two basic terms used to describe humidity are absolute and relative. Absolute humidity is the actual amount of water vapor in the air. It's often measured as ounces of water per cubic foot of air. Relative humidity is basically a ratio of the actual amount of water vapor in the air at a specific temperature to the maximum amount of water vapor that the air could hold at that temperature. Relative humidity is expressed as a percent of the maximum amount of water vapor that the air could hold. Measuring and controlling humidity is important because humidity can affect moisture-sensitive materials that are used in a process, as well as electronic equipment used to monitor and control the process. An analytical variable that's similar to humidity is moisture. Moisture is a measure of the amount of water absorbed by a solid material. Moisture can be measured in ounces of water per pound of material, but it's more often measured as a percent of total weight. For example, a moisture measurement of 10% means that 10% of the weight of a material is attributed to water. So if there are 100 pounds of material, there are 10 pounds of water. Many process systems are designed to use materials that have a specific moisture content. If the moisture content of a material is too high or too low, problems can occur with the process equipment or with the product being produced. Accurate moisture measurements can help prevent these problems from occurring. Different measuring devices can be used to obtain absolute and relative humidity measurements. Three devices that are commonly used are a sling psychrometer, a recording psychrometer, and a hygrometer. A sling psychrometer is typically used for spot checks of humidity in the air. This particular sling psychrometer consists of two thermometers that are mounted on a frame with a handle on one end. One thermometer is called a dry bulb, and the other one is called a wet bulb. The wet bulb is partially covered by a wick soaked with water. To obtain a humidity measurement, the psychrometer is slung through the air for about 20 seconds. During this time, water evaporates from the wick of the wet bulb, causing its temperature to fall below that of the dry bulb. The wet bulb's temperature drop depends on the evaporation rate of water from the wick. The more humidity there is in the air, the less evaporation there will be. The temperature readings from the wet and dry bulbs can be converted to a humidity value using a humidity chart. Spot check humidity measurements aren't always adequate. Sometimes continuous measurements are required. When this is the case, a recording psychrometer can be used. A recording psychrometer, like the one seen here, has a dry bulb and a wet bulb with a wick. The wick is partially immersed in a reservoir of water, which keeps it soaked. A forced air supply created by a small fan causes water to evaporate from the wet bulb's wick, reducing the wet bulb's temperature. A recorder maintains a permanent record of the wet and dry bulb temperature measurements. As with a sling psychrometer, the temperatures from a recording psychrometer can be converted to humidity values by using a humidity chart. Also, some recording psychrometers can process wet and dry bulb temperature information to produce a humidity value that can be read directly from the recorder. Now, another device that can be used to measure humidity is a hygrometer. A hygrometer operates on the principle that certain materials, such as hair or wood, expand or contract according to the amount of water vapor in the air. The hygrometer represented here consists of several strands of hair stretched between two posts. When the humidity in the air increases, the water content in the hair increases as well. This causes the strands of hair to stretch, moving a pointer up a scale that indicates relative humidity values. When the humidity decreases, the strands of hair contract and the pointer moves down the scale. During many processes, it's necessary to measure the moisture content of a solid material. Different methods can be used to do this, but one method involves the use of an instrument called an infrared moisture analyzer. Here's a simplified illustration of an infrared moisture analyzer. Simply put, the analyzer's operation is based on the fact that water will absorb certain infrared waves. During operation, the infrared waves are directed through a series of mirrors to the surface of the material being tested. Moisture in the material absorbs some of the infrared waves, but some of them are reflected up to a concave mirror. The mirror then directs the waves to a light-sensing photocell where they're measured. An indicator that's connected to the photocell displays the measurement as an indication of the moisture content of the solid material. The more moisture in the material, the fewer reflected waves, and the higher the moisture reading on the indicator. In this topic, we talked about what humidity and moisture are, and we looked at different ways to measure them. Now let's try some practice questions that relate to this material. Two basic terms used to describe humidity are absolute and relative. Absolute humidity is the actual amount of water vapor in the air. It's often measured as ounces of water per cubic foot of air. Relative humidity is basically a ratio of the actual amount of water vapor in the air at a specific temperature to the maximum amount of water vapor that the air could hold at that temperature. A hygrometer operates on the principle that certain materials, such as hair or wood, expand or contract according to the amount of water vapor in the air. During many processes, it's necessary to measure the moisture content of a solid material. Different methods can be used to do this, but one method involves the use of an instrument called an infrared moisture analyzer.